David Green from Wellmaster Corporation. And I'm here today to talk about some fundamentals of gas-driven well loading and unloading. We're going to spend a bit of time talking about the real fundamentals in how gas-driven wells operate and why we have issues with liquid loading, which ultimately affect production. Oftentimes these courses, classes have been built around the idea of deliquification of gas wells, and especially when it comes to plunger lift. But increasingly plunger lift are being used not only in gas wells, but in liquids-rich wells in all the major plays around the world. It's important to think about it from that standpoint because many of these wells are essentially oil producers, oil wells, some which may be operating with gas lift or rod lift, and perhaps plunger lift hadn't even been considered, but we're finding that today plunger lift has a much broader applicability than perhaps what we imagined or had experienced many years ago. So over the course of a couple of these types of sessions, we'll talk about how we apply these fundamentals to operating and optimizing plunger lift wells. So one place to start in thinking about all of this, especially if we're thinking about optimization, is what is an optimized plunger lift well? There's many definitions, and it can be a combination of things, but everything from a well that is running consistently to a well that is producing the most that the well can produce, to a well that is operating at its lowest cost. Each individual operator needs to understand what is driving their decision-making around their wells. We are primarily going to be focused from a production standpoint and in terms of trying to get everything that the well can produce reasonably and cost-effectively. Liquid loading is something which has been certainly well documented and well described in the literature over time, and the esteemed Dr. James Lee came up with this particular diagram many years ago, and it describes what is going on in a well as the well depletes from an initial production rate to some production rate later in the life of the well. So when that well is brand new and it's young, it's strong, we have a very high flow rate and initial production rate. We have a very high velocity of gas, or relatively high velocity of gas throughout the depth of the well. And that velocity is carrying the liquid to surface. So in natural flow, now we talk about artificial lift, but in natural lift or in natural free flow, the well is evacuating all the liquid out of the wellbore by virtue of the velocity of the gas. So think of it as a wind blowing up a pipe. If that wind is blowing strong enough up that pipe, then it will take that liquid up and out of the well. But of course our wells deplete over time, and as that production rate falls off, bottom hole pressure is dropping as we deplete pressure out of the reservoir. Rates drop off, and we start to see accumulation of liquid. The liquid builds up from the bottom of the well and starts to collect at the bottom of the well, and it starts to exert hydrostatic pressure back against the formation. Therefore, as this rate drops off and liquid accumulates more and more, actually the height of the liquid is reinforcing this reduction of flow into the well. And over time, we can see that the well will reach a point where it becomes unstable, or in some cases we would see this as slug flow at the surface. If we continue to flow the well, we can flow it out until it becomes stable again, where we get dispersed bubble flow. And just think of gas just percolating up through that liquid column. It's very ineffective at moving liquid. It produces a small amount of gas, but it could flow in this condition, in a stable condition like this for quite some time, and eventually the well will die. So we're looking at a couple of things. We're going to revisit this slide in a few more slides, but I wanted to get this in our minds first and foremost because this progression of liquid loading, which is depicted in the illustrations behind the rate curve, are important to understand and internalize when we think about our wells. I mentioned that this is initial production, and if we were just free-flowing a well, this is what we would expect if we had no artificial lift whatsoever. But at any time in the life of the well, when we are free-flowing the well, and it could be after a plunger has risen to surface and taken all the liquid away even, where we're in afterflow and we have a high flow rate afterwards, we still have a reduction in rate through the rest of the cycle in which liquid will start to accumulate in the same fashion. So the onset and the progression of liquid loading looks the same in every case, whether in any free-flowing case over some period of time. Okay, let's talk about the principle of plunger lift. I guess in my experience in the past in taking and studying at schools and being in many classes, especially at the beginning of my career in plunger lift, I learned a lot about pressure being the driving force in driving plungers. And I think one of the most important realizations for me came when I realized that I needed to think about plunger lift and any gas-driven well as a pneumatic system. We are using gas to drive it. It gives us an advantage in several ways. One of which is we have this power of the pressure in the reservoir, in the formation, and the compressibility of that gas to store kinetic energy. And we can release it in a manner that we can use to lift liquid or a plunger. The plunger acts as a physical interface between the liquid above and the gas below, and that minimizes drop back and makes more efficient use of the gas and of the energy that is in the reservoir. Now, it's interesting to note that plunger lift originated as a way to augment intermittent wells. So, unloading gas wells, if we go back 30, 40, 50 years, was often a matter of flow the well up, and as we saw in the previous illustration, until it loads, shut it in for some period of time, hours, maybe days, maybe longer, and then vent the well or flow it down line in an intermittent fashion and just let that pressure and gas flow and gas velocity carry the liquid out of the well. But today we use everything from continuous run and combinations with gas lift to expand the use of plunger lift. But essentially they're all just variations of this theme of it being a pneumatic system. So I'm going to say it's easy to understand. If we think about a job where we might need to paint a fence or a wall or some object, and we have a paint compressor with a sprayer, a spray gun on the end. And I think, well, I'm going to get a big enough compressor that I'll be able to spray paint this well, and that's going to happen in no time at all. Well, this compressor, let's think of it as Mother Nature's compressor deep in the ground. If that compressor is big enough and strong enough, powerful enough, Mother Nature's compressor is big enough, it will allow that well to flow very well. It will allow the well to remove liquid very easily. And, in the case of my paint sprayer, no problem at all. I can get that done in no time at all. But one of the problems is that Mother Nature's compressor gets smaller and smaller over time. And that just means that the well is being depleted, that the formation is taking, or at least has less and less energy available to help drive our system. And that creates some problems. And if I were painting my fence, it would probably take a lot longer with a smaller compressor because it has to work a lot harder, and it just doesn't have the capacity. When our well doesn't have the capacity, it challenges us here as well. Okay, we'll come back to that diagram of Dr. Lee's, and this is what I mean. The Mother Nature's compressor is getting smaller and smaller and smaller over time. The delivery rate of gas is reducing. The velocities are reducing in the well. I started to talk earlier about the accumulation of liquid. And that accumulation of liquid occurs for two reasons. We have gravity, of course, which is trying to hold the liquid down in the well. But the primary thing is we do not have sufficient gas velocity. So our gas velocity here is very high. Here we see we have high gas velocity in the upper part of the well, but a lower gas velocity down lower. And that is what becomes progressively worse and worse. And it's important to understand that there truly is a difference in velocity. Gas velocity, even in this case, is always lower at the bottom of the well than it is higher up in the well. And we reach a transition point, which is some measure of what's called critical rate or a critical velocity, and a transition point at which there isn't sufficient velocity to lift the liquid. So here we see this is where this transition point takes place. A little later in the life of the well, that transition is up a little bit higher. But we can see that we obviously have a much greater liquid holdup increasing as we have decreasing gas rate. So this implies some things which are very, very important from a production standpoint. And I like to say, well, we're out there fighting the good fight to be able to try to increase production and manage our production. So we better understand what the battle is really all about. Because ideally, we would love to maintain flow conditions like this. But over time, any time that the well is allowed to flow out for an extended period of time, it's drifting in this direction. It is accumulating more and more liquid to the point where it just wants to basically kill the well. Here we have a relatively low flowing bottom hole pressure and highest inflow from the formation. In this case, we've increased the bottom hole pressure and we have the lowest inflow from the formation. Obviously, we would really like to be closer to this end of the spectrum than the opposite end of the spectrum. And if we really want to understand what is causing the problem, it's the height of the liquid column. That is truly the enemy of production. So why is liquid height the enemy? Well, let's just take it down to something relatively simple, and that is hydrostatic pressure. So hydrostatic pressure P equals rho GH, where rho is liquid density, G is the gravitational constant, or acceleration due to gravity, and height, H, the height of the liquid column, is the main variable. Excuse me. Liquid density, the produced liquids do not change or change very little over the life of the well, typically. Gravity, the acceleration due to gravity, is obviously a constant, but the height of the liquid column could be highly variable. And that means that any variability, or the majority of the variability in pressure P, is solely due to the change in H. Excuse me. And therefore, height is really the only variable that we have any control over, this height of this liquid column. Whatever we do to manage that height of the liquid column is going to be effective, or our most effective means in managing production. Talk a little bit about why it's the height, because every once in a while I find that we have the sense that it is either the volume of liquid or the weight of the liquid column. This is a term I used to hear a lot many years ago, and still occasionally comes up as I teach my classes. But it is truly about the height of the liquid column. And this harkens back to the famous Pascal demonstration from 1646. Blaise Pascal, famous French physicist, came up with the idea of understanding that it was the height of the liquid column. And the famous experiment of Pascal's was to take a wine barrel, which is very strong, and fill it with water, and then to insert a tall, skinny tube, and begin filling the tube. Pascal began filling the tube, and when he reached a height of 12 meters, or about 40 feet, the barrel burst. Now, this particular quiz test says, calculate the mass of water in the tube in kilograms, and calculate the net force on the lid of the barrel just before rupture. Well, we'll jump straight to the answers here. And how much water was in the tubing? What was the weight of that water? Well, it was just under a half a kilogram, or just over 1 pound of water. So was it really the weight of the water, the mass of the water that broke the barrel? No, it was not. It was the height. And what about the force that was acting on that lid of that barrel? Well, if we calculate that out based on the diameter of the lid of the barrel, we can see that that force was over 3 tons, or almost 7,000 pounds of force. So no wonder the barrel broke. And all of that from a mere 1 pound, or under a half a kilogram of water. And if we think of a little standard water bottle that we might carry around or purchase at a store, those are typically about 500 milliliters, or a half a liter. And a half a liter is a half a kilogram, which is about that. So think again, if we had a small water bottle and we were to imagine trying to break a barrel with that, we'd be very hard pressed to think about how we could possibly do that. But there's a huge amount of potential energy in that little amount of water if we were to make a liquid column tall enough to be able to create that force. Rho GH. H is important in creating that force. So the real task, and I hear this a lot, of course, and I think it's very common that people know, let's say, that we need to reduce the flowing bottom hole pressure. It's not always about getting to the lowest flowing bottom hole pressure, which we'll talk about in a moment, but the important things to remember are that flow of any gas or liquid can only occur, or flow from one point to another can only occur if there's a pressure difference from point A to point B. So if we start out in the formation where we have a pressure, and we have another pressure over here, bottom hole, inside the wellbore, we can only get flow from here to here if there's a pressure difference. So that is key and fundamental. And we want to know that we have maximum flow into the wellbore if that bottom hole pressure inside the wellbore is greatly different, or much, much lower than that in the formation. And we could speak about a theoretical open hole flow, which is the condition where it would be if we reduced this pressure inside to zero. We would have absolute maximum flow. If we had zero pressure bottom hole, then we have the maximum pressure difference across the perforations. If, on the other hand, we were to allow this pressure to rise, so that we put enough liquid in the well that this pressure bottom hole is increased by the hydrostatic pressure so that it is equal to the formation pressure, then we could actually take the flow totally to zero. And this is exactly what we just witnessed with that progression of liquid loading. Went from a maximum flow rate with low bottom hole pressure to zero flow rate when we had a high bottom hole pressure. Now this is well understood and can be well explained with an IPR curve, or the inflow performance relationship curve. So here's just an example of a well with 6,000 psi of static bottom hole pressure, and then the formation gas rate, and how those two relate to one another. If we are operating at a certain pressure, let's say we have a flowing bottom hole pressure of 3,000 psi, it gives us a certain flow rate. If we were able to reduce that flowing bottom hole pressure, we can see that we come across to a different point and we see a significant increase in production. So this is very clearly the relationship between flowing bottom hole pressure and formation gas. And it is key in understanding this relationship as we manage our wells. It means that we need to manage bottom hole pressure. Okay? Now, we could say, well, why don't we just bring it all the way to zero? And we would have that absolute maximum. At some point, usually before this curve breaks over, we will reach a point where it's very difficult to maintain stability of the well, or stable flow. And there may be more of an issue from an optimization standpoint of the well going down for one reason or another. Keep in mind that this pressure at the bottom of the well is also important relative to the surface pressure, and that if we take away too much of that drive, then we just may not have sufficient drive to operate the well continuously. It may become very erratic. It becomes much more sensitive to upsets in line pressure conditions, or varying liquid inflows across a lateral, let's say, in a horizontal well. So we want to have some robustness, some stability built in, or the ability to maintain stability built in. So we will usually try to optimize to some level in this area. This whole concept of pressure management is very, very important. And this is a slide I obtained from Texas A&M, I believe. But in any case, it is looking at the pressure in the system on the y-axis versus its position in the system on the x-axis. And we start out at some boundary of the reservoir, and this is our pressure drop across the reservoir. So we're moving position in this direction. We get into the completion, which is perhaps where the limits of our frac, other aspects of our completion, until we come to where our wellbore ends, and then we are managing pressure. And there may be some things in there, for example, tubing restrictions that cause a sharp, it might be small, but a sharp drop due to some restriction, perhaps some scale, or we may have paraffin buildup, accumulation in the well. We may have something like a safety valve or an intermediate nipple, something that gets in the way that gives us another pressure drop. We get to the surface, and we have our wellhead through whatever our wellhead piping is, surface piping is, through the choke, and then across to whatever our desired delivery point is. Here it's referring to the separator, pressure at the separator. So it is a case of trying to manage pressures all the way across the system. Well, what do we have control over? Well, we do have control over those restrictions and limitations at surface. We have, in normal production situations, we don't have any control over on this side. And here's the part that is in the middle, from the end of the tubing through to surface equipment, that we are attempting to manage here. We have to be keenly aware of this, and the amount of liquid, not just that height of a static fluid column, but the total amount of liquid that is held up in the production tubing, even under flowing conditions, impacts this pressure profile. And that's what we're attempting to manage. Sometimes it's hard to visualize that small amounts of liquid can have huge effects. If I said for a moment that I'd like you to stand downstream of this dam while I lower the pressure in the lake by 10 psi, I'm going to do that very quickly and suddenly. Perhaps, if I said this was a good day for fishing, it would be a great time to stand out there and catch a few fish. However, 10 psi drop in the lake pressure, it's measured at a point at the outlet of the dam, may not sound like very much. And we might say, hey, that's not a bad idea to go fishing in that river. But if I phrase this a little bit differently, and it's a freshwater lake behind a dam, and I said instead that I'm going to lower the height of the liquid, the water, in the dam by 23 feet. I'm going to open this up or do something with my outlet to drop this level as fast as possible. Then the whole idea of standing in the river, fishing or boating or whatever sort of leisure activity we have in the water that day probably doesn't sound like a very good idea, because we know in our mind's eye now that we're most likely to have a big rush of water. A 23-foot drop in that height of that liquid column is going to be a massive amount of liquid that is water that's going to be released. And so when we are operating our wells, think about dropping the height of the liquid column or dropping the height of the dam, let's say, equivalent, in our wells, or raising it. And what that does for the flow rate coming out of or across the perforations, because that's essentially the same thing that we're doing here. And this has implications not only in vertical wells. I've been speaking mostly about vertical wells, but today, of course, we are increasingly getting into a horizontal and unconventional world. And so it has application there. It has some meaning. So, for example, if we were to think about pumping or setting our bottom hole assembly at a kickoff point on this horizontal well, we are perhaps missing out on an opportunity to reduce the height of the fluid column in TVD terms by coming down and setting our tubing and our DHA at lower points. So at 45 degrees, for example, and this is just from a very typical drilling survey, I got these figures from, that at 45 degrees in this case, there's a 450-foot TVD difference from the point at which we can remove liquid. And our perfs are down here. So we are reducing the height of the liquid over the perfs by pumping from points closer and closer to that in TVD terms. And at 45 degrees, depending on what the makeup of the liquid is, it could easily be 150 to 225 psi additional reduction in flowing bottom hole pressure. And that's an opportunity to increase production from the well. At 60 degrees, that range is even higher, and I'm showing 240 to 360 psi of potential pressure drop. And that has enormous consequences for the productivity of a given well. It's true in vertical wells also, although with plunger lift we have to be careful that we don't set too deep in a vertical well. It's funny, over time, I've seen that there was an old adage of rule of thumb, let's say, of where to put land tubing in vertical wells, and it was always anywhere from the top of our top perf to 1/3 of the way into the total perforated interval. And that rule of thumb has really been validated over time. We did a study with a customer a few years ago, and we tested various depths. They had actually very deep set tubing, their plunger lift was struggling, and we ran tests on about 30 wells, and in some of the initial wells we were perforating tubing at about 50% into the perfs. We got some improvement, but really still had very unsteady flow conditions. Over time, it was very interesting, but it migrated to about a 33% into the perfs, was just about perfect across the board. Gave very, very good uplift and much improved performance overall, ease of operation, etc. So optimized in many, many respects. Here again, we see a version of the IPR curve, and I put this up because what we often see, and I see this very, very frequently, is that wells are often very sub-optimized and even have operating difficulties. If we are allowing this bottom hole pressure to build, and this is showing the pressure as a ratio of producing bottom hole pressure to the static pressure, but it will be quite sub-optimized. But very often we also see, well, a well is running extremely well. The plunger is going up and down. It doesn't miss any trips. We're not breaking equipment or tearing up equipment. So it must be optimized. And that sometimes is, I would say, it meets some criteria of optimization. Let's say from the ability to keep the well in operation, that it's steady, it's reliable, and it's not a headache. It doesn't take any excess time to keep the well in operation. And yet, if we were able to lower this flowing bottom hole pressure, we would see that this curve shifts. So much like we saw in the previous illustration of the inflow performance relationship, or IPR curve, it's still driving us in the same direction. Lower flowing bottom hole pressure will result in improved production efficiency. And this is from the inflow standpoint. So we're only talking about what we're bringing in at the tubing intake. That's what we're really trying to pay attention to. All right. So one of the things that I heard many times over the years was that we have to have the lowest flowing bottom hole pressure. We just discussed a little bit about some of those reasons, but I can categorize a few of those here and list them for you. Reservoir management being first and foremost. We are trying to manage these reservoirs to produce in the most efficient and most effective way. Early on in the life of the well, in particular, if we are pulling the pressures down too quickly, we may have excess flow rate into the well bore. This will bring in sand, frac sand perhaps. If we create damage in the formation by pulling that out, sometimes here in North America we talk about it gutting out the frac. We don't want to do that, because we spend a lot of time and effort and money to fracture our wells and to complete our wells this way, and washing out that frac sand is problematic. Another is where they're in a vertical wells in particular, where we have multiple zones over a horizontal interval, and they may have different gas to liquid ratios for those particular formations. They may also have their own, let's say, threshold pressures at which they hold back liquids and below which they release liquids. So we have to be very careful as we pull our pressures down that we don't pull them down so fast that we flood the well out. In horizontal wells, across the lateral stages, the well may not be perfectly flat. We call it a horizontal, but that doesn't necessarily mean it's flat. And quite often it could be toe down, it could be toe up, it could have various shapes along the lateral, which also can unload differently at different pressures. So we want to manage that pressure. As I said earlier, excess flow rate may draw in sand, but in most of these cases it means that there's a minimum bottom hole pressure in at any given point in the life of the well that is somewhat ideal for the well at that point in its life. And we want to not only prevent holding back our production, but we also want to be very careful that we don't have excess inflow. All right, why and when would we install plunger lift? We talked a little bit about the liquid loading aspects here, but we're going to put in plunger lift as part of our artificial lift strategy. What are the types of things that are going on in the well that would trigger that occurrence? Well, the primary one in a gas-driven well is that there isn't enough gas velocity to lift the liquids. Think back to Dr. Lee's illustration. At the far left, we had plenty of gas velocity that was carrying the liquid up and out of the well. At some point, the well is going to deplete to the point where it is flowing below some measure of critical rate. Now, we'll talk about critical rate separately here in a moment, but it may or may not be what you're thinking from a critical rate standpoint. So we'll talk about that. Plungers are also very good mechanical cleaning devices. They can be used to keep a well, the tubing clean. Now, we are seeing this particularly in liquids-rich plays. Paraffin is very often a problem. Will accumulate and start to block off the flow path through the tubing. A plunger can stay ahead of that. It can eliminate or reduce the amount of chemical mitigation that we have to do, the amount of wax scraping we might have to do if we're using mechanical scraping means. It can help in many, many ways, and we can stay ahead of that paraffin. Same thing goes for sand and scale. We can keep those elements clear off the tubing. Once we have the tubing cleaned up, the plunger can maintain that tubing in good operating state. We should always install this prior to production falling off the normal decline curve. This is an important thing to consider. Let me just sketch here for a moment what I mean by that. And if we look at production over time, we will have, I'm going to call a natural decline of the well as it goes through its life. And at some point in time, the well will free flow for some period of time, which is wonderful. However, there will be a point where it starts to drop off and liquid starts to accumulate, and we start to see the impact of this liquid buildup, as we saw in Dr. Lee's illustration. And we will see erratic flow. Maybe we go like so. Maybe we have some days that are up above and some are below. But let's just say, for example, here, we have a 1-year period. And we've had some issues with the well. Due to this liquid loading, we can see accumulated periods below the expected and the natural decline. And if we sum all of these excursions below the line and we add on excursions above the line, which is very small in this case, we can see that over the course of a 1-year period, we have a net loss of production. And that truly is a loss. We need to be clear in our minds that we do not have the rest of the life of the well, because this is where this will come back, is we only tack it on to the end of the life of the well. We don't want to wait that long to get that production. We want it here. So the idea of when to install plunger lift, and traditionally, if I think back over the years, was people waited for this situation to occur. And then at some point, it's, well, we have to fix this. Let's finally put our plunger lift system on and all is good. However, there is these cumulative losses over a long period of time that may or may not ever be recovered from this well. So timeliness of intervention is very, very important. And what we might do instead is recognize when this condition is going to begin occurring and start to intervene and add our plunger lift at this end of the life cycle of the well. And we might here run, for example, today, in today's world, we might run a continuous run plunger. After some period of time, perhaps we have to switch to something else like a quick cycle plunger or fast cycle plunger. There's a variety of types. And then as we move further along, we're switching to things like bar-style plungers, pads, etc. But we can manage this. We can manage to avoid losses by recognizing that we need to act sooner rather than later. It pays for us to act from a production standpoint, and that over the life of the well, we probably will have to change our plunger style and type that we use that will be suitable for the well under the flowing conditions at that time. All right. After we install plunger lift, and let's say we see some uplift as a good news, good example right here again. What if I put in my plunger lift down here late in the life of the well, and I got a big bump in production? Eventually that production is going to stabilize at the natural decline of the well. And I might see a big bump up here for a little period of time, some flush production, for example. But if that gain is less than what our losses were here, we're still over this period in a net loss position. It would have made sense for us to act earlier. So we should always say, yeah, the uplift is always good news. We'll always take that. However, were we timely in when we made the decision to install our plunger lift system? Okay, we talked a little bit about critical rate, or I mentioned that earlier, and critical velocity. Let's understand what that really means. And if we come back to the theory behind this, and you look at the work done by Turner back in the 1970s, I believe, all of his theories and his experiments, etc., were all based on developing a droplet model. So here's a cross-section of a piece of tubing or a pipe, just say it's pipe, and we have gas flowing up through this pipe. We have liquid, some of which is deposited on the side of the tubing. It's a fully mixed or highly mixed and wetted setting, and we have droplets of liquid, let's say like mist form, etc. We can describe it different ways going up through the center of the well. But let's just take a droplet aside for a moment and look at the forces that are acting on this in this environment. One of which is gravity, of course, which is ever present. And gravity is going to try to pull that droplet back down into the ground. And we're going to try to counter that with a drag force. The drag force is just a function of this wind, the gas, blowing past the drop and trying to draw it towards the surface. And it's kind of a tug of war, a pulling contest in the vertical sense between these two forces. So if the gravity force is greater than the drag force, obviously the droplet is going down. And if the drag force is greater than the gravitational force, then the droplet is going up. But what if the drag force and the gravity force are exactly the same? Then our droplet is suspended. It's suspended in space. And that is actually the definition of critical velocity. It is the velocity of gas that suspends a droplet in one spot. So it's not actually moving up or being carried out of the well. Oftentimes people will say, I'm flowing at critical velocity, so I'm unloading my well. That's not true. The fact is, critical velocity is telling us that's when all motion of these droplets stops. It's a very important concept to have clear if we're thinking about would say that everything that falls by gravity in a given environment has a critical rate or a critical velocity. A skydiver jumping out of an aircraft, plummeting towards the ground, falls at a speed of about 120 miles per hour if they're in that famous skydiver position. About 120 miles per hour or about 200 kilometers per hour. And if we were to do this in a controlled environment like indoor skydiving, which is what this depicts, if we have a wind blowing from below, that speed simply has to match the free fall velocity of that human being in order to suspend that person inside this indoor skydiving facility. So, in this case, we have our gentleman conveniently hanging in space. We know if he's not moving up or down, if he's stationary, suspended, that the wind speed must be equivalent to his fall speed, or about 120 miles per hour or 200 kilometers per hour. This is exactly the same as it is for our little skydiving droplets. Okay, so it is important that if we are going to evacuate liquid using gas velocity, then that gas velocity must be above whatever that critical rate is for that droplet. All right, we can get different types of flow in vertical pipes. And here's some examples of below critical rate. One being dispersed bubble, which we touched on earlier. Often just with, after a well is very highly loaded, we might see this situation. We might see it in very low GLR wells. Slug flow, we'll get these various big separations of slugs of gas and liquid. And sort of an in-between one that doesn't really get talked about very much is called Taylor cap bubble, but it's sort of a blend of somewhere between these two. And then at or above critical, what people are usually looking for is what they call annular/mist flow. And that just means that there is mist flow up through the center, and there is a liquid layer or liquid film which is attached to the surface of the pipe. And that is there because of friction and the fact that the velocity is at least theoretically zero at the surface. So our gas velocity, our liquid velocity is theoretically zero right at the surface, and we accumulate some thickness of a liquid film or layer on that surface. There's different ways of looking at this. This is just a quick example of the Pellis-Aziz mechanistic model, something that I looked at a very long time ago, but looking at the velocity of the liquid versus the velocity of the gas, and if you vary these rates both up and down in relation to one another, you can get these various forms. So here we have the annular mist region over here, where the velocity of the gas is high enough. That's really what this is representing. And as that gas velocity drops off, we get various other flow regimes that can occur. But what's important to understand, I think, from a critical rate standpoint, is it's not just so simple that above a certain rate, you're lifting all those liquids, and below a rate, all those liquids are falling down. And there's a couple of reasons behind that. One of the basic reasons behind this is that there are transition areas where our droplets, and remember this is a droplet theory for the Turner critical rate and the Coleman critical rates, but the gas and droplets can theoretically and realistically be traveling upwards, and yet this liquid layer becomes a very important and dominant part of liquid removal, and whether or not we're affecting liquid removal. And we can actually have liquid reversal and reverse flow at the surface, or on that inner surface of the tubing. So in a free-flowing state, we might see this as the casing pressure flattens out, starts to increase. It means that liquid is dropping down. Or as casing tubing differential increases. That is actually an indicator of liquid holdup in the tubing string, even under free-flowing conditions. We tend to think of that differential pressure as being representative only of amount of liquid in the tubing over that in the casing in static conditions, but in flowing conditions, it still is representative of the amount of liquid that is actually held up through the entire tubing string. It's something we need to pay attention to. And if we look a little bit deeper as to what's going on in this flowing conditions, it's not as we saw in this slide. This is a very nice, convenient slide that just says that we have this liquid layer all the way up the tubing, but it isn't actually as simple as that either. And some other studies that have been done. This was a study that was done a few years ago I believe it was part of it was published in the Journal of Petroleum Exploration and Production Technology in 2019, but it talks about, if this is a half section, so we could mirror this to get the full diameter of the tubing, but we have gas represented by these vectors, and we have liquid represented by these vectors in terms of the velocity and what that liquid is doing, the direction and relative velocity. And we see that we have some liquid reversal. We get kind of waves, just like you would across any liquid surface. If we were to blow wind across a lake or a pond, we would get some wave action. And if we blow harder, we get perhaps some white caps or some frothy surface. And that frothy surface might shed some liquid. We would call it spray if we were standing there by that body of water, but inside we get the droplets getting created and re-entrained into the gas flow. I have a CFD simulation that was done by these same people that did the previous paper, which is quite interesting in that it is a computer simulation using computational fluid dynamics to illustrate what is happening, or at least what that flow looks like in this pipe. And these are, excuse me, liquid volumetric fraction. So blue is low, means it's mostly gas, there's very little liquid. Red, we see here on the tubing wall, is a high liquid fraction. It's mostly our liquid. In this case, I think they did it with water. Yes, it was an air-water mixture. And let me see. I should be able to start this. And we can see this. If we looked at a half, we can see this wave action and this kind of frothing or shedding of droplets off the liquid against that surface. And this is just a few seconds long loop, but it gives us an entirely different kind of perception of what's going on in that flowing tubing than we saw from the static illustration, which is historically the way this has been represented. Okay. And when we are dealing in our wells, we have or working with our wells, it's very important to remember that these various flow conditions, flow regimes, etc., that I talked about can all exist in one flowing well from the bottom to the top of the well. And you might ask, well, how is that possible? If I have steady state flow of gas and liquid coming out of the surface of my well, how can it be that I have different flow regimes in the pipe? And the answer to that is in the compressibility of gas. So our gas is compressible, our liquid is incompressible, or virtually incompressible. And so we can have very little liquid. Here it talks about single phase deep, we reach a point, the bubble point, where gas starts to come out of solution, and as it goes further up in the well, those conditions start to change, and we might get to, in this case it talks about slug flow, but we could have a significant gas flow at surface and very little gas flow deep down in the well. And that compressibility becomes a very important consideration as we try to design for optimized conditions in our wells today. And this is just another illustration which talks on the same topic, perhaps even more extreme, but where we have some gas already introduced and coming from the formation down low, and where in the upper part of the well it is actually showing mist flow. Okay, but those conditions can be very different from bottom of the well to top of the well. Now, these examples or these illustrations I just showed you assume that we have single-phase liquids, which often, or most often, is not the case. There's usually some presence of one or the other. So we might have a well that makes mostly oil or condensate, but there's usually some water cut there. Conversely, in a gas well that is a dry gas well, we might have virtually 100% water, but usually there's at least trace amounts of condensate in there as well. Also, these are assuming a constant flow rate, and we, in plunger lift case, have varying flow rates. So if in a conventional well, for example, or a conventional operation where we're shutting in to let the plunger fall to bottom, we're waiting some period of time to build pressure, we open its surface, the plunger comes up, we're getting a certain flow rate. With that head gas coming above the plunger, we're starting with an inflow rate, so we've got different flowing conditions, we've got lower pressures up high, we have more gas expansion, and there's going to be this difference across the bottom to top. And then after the plunger arrives, we're going to go into afterflow, and that afterflow rate will drop off over time, and that whole change in flow regimes is going to change, and it's going to be a dynamic change through the cycle. Okay. The other thing that is very important is that as we get into horizontal wells or S-shaped wells or any kind of inclination in the wells, that it also adds a layer of complexity in this flow and how our well unloads by itself and how the plunger will travel in the well too. One important consideration related to this gas expansion is that this, for example, is a plot of our velocity versus our depth, okay? And here we have a well that's 11,000 feet deep, and it's a very wet well with has a lot of liquid. We're in that sort of 200 to 300 barrels per million range, and free-flowing conditions, let's say, or at least that's what's modeled here. We see very low gas velocity down deep in the well, and then it sort of breaks over as it comes to surface, and this gas comes out of solution, and the gas expands due to the pressure difference, and we have a very high gas velocity towards surface. We've seen circumstances like this where people have tried to run plungers, and they think, well, when I open my well at surface, I hear a very high gas flow rate. My plunger should be running. And yet, deep down in the well, we have a very low gas velocity. And I'm going to tell you that it is gas that is moving our plunger. It is not pressure. Pressure differences, things that we use in terms of kick-on parameters that use pressures, whether that's a casing overline, a tubing overline pressure, load factor, Foss-and-Gall, all these pressure-based calculations are really about trying to generate conditions at the bottom of the well that are adequate to fly the plunger. So I want to start using the term flying the plunger as opposed to pushing the plunger with pressure. I think well, I know that it correlates better to how plungers actually travel. So in this example, there was really no pumping effect because the gas velocity was too low. The gas in our pneumatic system was not sufficient to drive the plunger or push the plunger or fly the plunger so that it could lift the liquid. And so we struggle with our plunger down deep. And we might have to think about this well in a very different way. So issues that we have, and this is very common with lower GLR wells, for example, or in any wells that have a very high pressure difference between bottom hole and surface. And we also see it in cases where we are running gas lift in conjunction with these wells, or even gas lift on its own for that matter. And in plunger-assisted gas lift wells, or PAGL, or what's it called, PAGL or GAPL wells. And we might have conditions where I've indicated here are very unfriendly for plungers, and that the gas can't drive the plunger. There just simply isn't enough gas in that overall mixture. So we have a situation where it can be very unfriendly down at the bottom of the well. Compressed gas occupies a very small volume. We have a relatively high liquid holdup. But as we move up the well, we can see that we get into a transitional area. And this transitional environment is where our gas is beginning to expand. It's taking up more of the volume. The gas is actually traveling a little bit faster now. And it is starting to be able to effectively move the plunger and actually pump liquids. And of course, as we rise in the well, that gas expansion continues and it occupies more and more of the volume. The whole mixture of gas and liquid starts to move faster towards the surface, and the plunger travels more effectively and can lift and carry those fluids up. So understanding these various changes in the flow regimes and just what that means from a plunger travel environment, a pumping environment, it's very important to understand that we can't just say, well, let's land our bottom hole spring assembly at the lowest point in the tubing and assume that we can pump from there. Sometimes we actually have to set our tubing stop or a collar stop for our bottom hole assembly at some intermediate point and to be able to lift effectively. There's no point in just having the plunger get pushed around by the fluids down lower, down here. Okay. With respect to loading again, I want to look at, predicting when and where and how loading occurs. So let's just talk about that a little bit. And primarily there are two forces that impact our two-phase flow. And primarily these are gravity, trying to hold the liquid down, and friction. So friction in the flow of the pipe. So that pipe is a relatively small diameter relative to its length. And when we try to move a lot of gas and a lot of liquid through that pipe, we can have a very high amount of friction. So with nodal analysis, we can create what is called a vertical lift performance or tubing performance curve, sometimes called the J curve. And it is represented by this solid black curved line, and it is a function of, or it is the sum of, this particular curve here, which is the pressure from friction in the tubing, added to the pressure from liquid buildup, or the hydrostatic load. So we have these two elements, which are the key contributors. And if we think about friction for just one moment, if the flow rate is very low, there's very little or no friction. As that flow rate increases, it makes sense that our friction would also increase. The liquid, though, and liquid buildup at a very high flow rate, friction is high and keeping the flow very, very turbulent, very highly mixed. The pressure from accumulated liquid is, or at least from the amount of liquid that is held up in the tubing stream, is actually quite low. And as the flow rate drops off, the mixing ability gets worse and worse. The accumulation of liquid on the tubing wall becomes more prominent. Flow reversal starts to occur, and we start to see pressure bottom hole building as a result of accumulated liquid. So at very low flow rates, friction is not doing a very good job of maintaining, let's say, a turbulent, well-mixed regime, but it also means that our liquid is very dominated by gravity, and it is getting pulled back down, and it is creating our bottom hole pressure. And that's, by the way, what this represents, is our flowing bottom hole pressure. So if we were to examine this J-curve or tubing performance curve in a different way, and this is from a program called PRODOP, which is an older nodal analysis program that was created by Dr. Lee a number of years ago. We were primarily using SNAP as our nodal program these days, but we can generate a J-curve, and here we see the friction side of the curve. I'm just going to call that the friction side of the curve, and this the hydrostatic side of the curve. And somewhere here in the middle, once upon a time, there was at least the description of loading versus unloading, or stable versus unstable flow. Everything to the right of the minima, at this point, the minimum point, was considered stable flow, and everything to the left was unstable flow. What we've observed empirically over years of looking at a very large number of wells and data sets is that that isn't necessarily true, not necessarily the case. So today, what we typically do is we look at this friction-dominated side of the curve, and we draw a straight line and say, okay, that is our 100% friction line. And then we look at this space, or this area here, where the tangent breaks away from the curve. And the reason that the tangent, or at least the reason the curve breaks away from the tangent, is we are now seeing a transition to hydrostatic contribution to this bottom hole pressure. Even though the pressure is not going up yet, it's bending this line because liquid is starting to accumulate. So this tells us that there is a place here which is very highly predictable and has empirically proven out to be very, very accurate, provided your modeling is done well, that tells us when this liquid accumulation on the tubing wall at the end of tubing starts to begin, because that's where our liquid loading begins, is at the end of tubing. And so we look at this area instead and say, aha, we have a different range where we have a transition from unstable to stable flow conditions. And this represents a very different gas rate than if we simply looked at the minimum. So in this particular case, it's around 1 million cubic feet per day versus about 650,000 cubic feet per day as predicted by the minimum point on the curve. And this is very important, both from the standpoint of when we would expect liquid loading to begin initially in a free-flowing well, or even the rate, this rate, instantaneous rate, that we would expect to see liquid begin to load in the afterflow portion of a normal conventional plunger cycle. And critical rate, as calculated by Turner, and this is just a set of typical curves that we saw in use for many, many years, where folks would look at what their pressure was at the wellhead. In this case, let's take 300 psi, and let's just say I have 2 3/8 tubing, which is represented by this line, and it says that I have a critical rate of about 550 MCF a day. A couple of things to keep in mind when we look at curves like this is the critical rate calculation that determines this curve is very much a function of this pressure. Now we say at the wellhead. Well, if we are only looking at the pressure at the wellhead, then we are only looking at what the gas flow rate is that is required to suspend droplets at the wellhead. What about downhole? What if downhole we had a much higher pressure? So instead of saying just at the wellhead, it's just really a function of this flowing pressure. What if my bottom hole pressure was 500 psi? Well, if I come out here and look at what that represents, we have about 700 MCF a day. So instantaneous rate. So that is telling us that our bottom hole critical, the point at which in a vertical well, that it would take to suspend droplets at the bottom of the well is 700 MCF a day. Yet it's only 550 MCF a day at surface, where our flowing well head pressure is 300. That has implications for our operations, and if we are only looking at surface critical numbers, regardless of the diameter of the tubing, we are missing opportunity because we may be, or we will be, underestimating what the loading conditions are deep down in the well. And we had a case a number of years back with a customer in Canada who switched in this philosophy from using surface to downhole predicted pressures in order to calculate their critical rates, which meant that they started shutting in sooner in afterflow. Plunger arrives at surface, we're into an afterflow period, and now we're trying to determine when do we shut the well back, or shut the well in to return the plunger to bottom and cycle again. Well, we want to make sure that we have enough fluid for the next cycle. We want to make sure that we don't flow so long that we just accumulate lots of fluid. And in this particular example, they went from, and using those bottom hole conditions, from a true daily rate average of 550 MCF a day, or 15 and a half decks a day, to 630 MCF a day. And at gas prices at that time, which are not far off where we are in the United States right now, that represented $80,000 a year in additional revenue. Were they able to maintain that rate? But that's what it represents on an annualized basis. So some real potential gains in understanding when liquid loading occurs, staying ahead of the liquid, keeping it evacuated, keeping that flowing bottom hole pressure low. Just going to touch on flow and horizontal pipes here for a moment. We'll talk a little bit about the impact of inclined tubing as well. So low gas rates, or low GLRs, we would expect conditions such as dispersed bubble flow, plug flow, what they call stratified flow, where there's a separation between the gas and the liquid layer. Stratified, wavy, I mean, there's all kinds of descriptions of these things. But you can actually get to a point, even in horizontal well, if you have a very high gas rate and or a very high gas to liquid ratio, where you can essentially get this mist annular condition. The situation with horizontal wells and flow and inclined tubing, why is that such a mystery? Well, all of our history, going back prior to the world of horizontal wells and with plunger lift, is that they were operated in vertical wells. And the knowledge here in a vertical well is actually quite good. So there's lots of experience, lots of years of operating, many rules of thumb that actually work out quite well. Horizontal sections, well, think about a pipeline on the surface. We have pretty good knowledge in the industry about how to understand and how to model pipelines. So we have pretty good knowledge here. The tricky part is this in here. The knowledge here has been quite poor overall. And when I say in here, I mean the entire heel in a horizontal, or I mean any highly inclined section of pipe. This could be in an S-shaped well also. We can have other issues with horizontal wells, of course, with toe up, toe down, sumps, that will carry liquid and make them operate erratic. And there have been various attempts from different researchers to come up with multipliers of the critical velocity, or in this particular case, predicting the actual critical velocity, not a critical rate, mind you, but a critical velocity based on the inclination angle. I would say that based on a study I saw by Dr. Lee about 1 year ago, or let's put it as in the spring of 2022, that the correlation of these various models was very inconsistent. And in fact, he, at the end of that particular paper, reverted back to the method I just showed you in examining the J curve or VLP curve, and found that to be much more consistent across the board in the examples that he tested that against. So in inclined tubing, why would we have a problem with Turner in inclined tubing? Well, it comes from the fact that Turner and Coleman are based on droplets falling against a gas flow in a vertical well. And so we're trying to, keep this droplet suspended. It's trying to fall vertically. Our gas is flowing in line with our... So the condition when the well is inclined, our droplet still falls vertically. However, our gas direction, if we look at this vector of gas flow, the gas is going in line with the pipe, and the droplets, let's say, accumulate on the low side of the tubing wall. So we get a different tubing, or at least a liquid layer thickness on this tubing wall relative to the surface. So we have this non-uniform film inclined on here. And the more this pipe is inclined, the more this is pronounced, until we really get a very high degree of stratification. And here's an example of a high GLR well from the Marcellus Shale some years ago with a customer that we were working with, and they took a section of pipe in the curve at about 45-degree inclination that was flowing above critical, according to Coleman or Turner, and yet they were having some scale issues. So when they pulled pipe, they sectioned the pipe and lifted the top half from the bottom half, and we could see these two beads of scale. And here we've just zoomed in and looked at it a little bit more closely. And what we had was water running down this lower center section of the tubing, and where the gas was interfacing against the liquid, we got formation of scale on the banks of that river. If we think about it as a little river down the center, then we were forming scale on that in that contact zone between the gas and the liquid. So the problems with using critical rate multipliers for inclined wells, they're kind of a hybrid of vertical and horizontal, and there is actually no critical velocity from the standpoint, or let's say the definition as given by Turner and Coleman, in terms of suspending droplets. There is no such actual critical velocity such as that. And decreasing the gas to liquid ratio increases the gradient, changes the position in the well where the transition takes place. We looked at that a number of different ways earlier. And in low GLR wells especially, we see the effective critical rate, that is the rate at which we actually begin to accumulate liquids, being much lower than what the theoretical rate is. So we're flooding the lower portion of the tubing, restricting open area, causing high gas velocity over the remaining space above the liquid, but that isn't sufficient to keep the liquid moving up the well. All right, thanks very much. That's all we have for today in this particular session. Next session, we will begin talking about actually choosing, selecting plungers and plunger operation. This is the first in the series of fundamentals. I hope it's been helpful. Please reach out to us at wellmaster.com, or contact me directly, David Green, at wellmaster.com.